Hello Internet! What did classical physics get wrong about the world? That's the topic of this episode, the second one in our series about how to understand quantum mechanics. If you haven't watched the first episode yet, please do so, because in this series each episode builds on the previous ones. I will link the first episode in the description below. In the first quarter of the 20th century, it became painfully clear that the theories of classical physics had deeply misunderstood how the real world works. Classical physics made embarrassingly wrong predictions about the behavior of atoms, which ultimately led to the complete experimental falsification of classical physics and around 1926 to its replacement by quantum mechanics. Still, although classical physics has been proven wrong in the most spectacular way, its mistaken assumptions are cherished by many. These often tacit wrong assumptions underlie a scientifically untenable realist worldview, which nevertheless is common and popular up to this day. In order to clarify our thinking, we therefore must examine the wrong assumptions of classical physics and the misleading worldview that hinges upon them. Before we continue, please subscribe and comment to support the channel. It really helps a lot. To formulate the divergent ideas of classical and quantum theories, we must first understand their common empirical foundation, namely the physical observation of the real world we experience. In the last episode, we looked at the simple example of observing a particle with position x and momentum p. We quantified the result of the observation in form of the real numbers x and p and their respective uncertainties, delta x and delta p, which are positive real numbers. So far, this is just a description of what we experience, and therefore it must be accommodated by any viable physical theory. What precisely do we mean by uncertainty? The uncertainties delta x and delta p express the limits of our ability to distinguish physical situations. When the difference of two x values is less than the uncertainty delta x, for example, we cannot claim to have observed two different positions. No matter which physical theory we use, as observers we must deal with uncertainty, because any observation only gives us a limited amount of information. It wouldn't make sense, for example, to claim that we have measured the position x to be exactly pi centimeter, or exactly 1 centimeter for that matter, because a mathematically precise real number, like the number 1, represents an infinite amount of information, while any real measurement has limited range and limited resolution. Note that the meaning of uncertainty does not depend on our physical theory. It is a common misunderstanding that quantum mechanics would introduce a new kind of uncertainty. It does not. There aren't different kinds of uncertainty. Uncertainty expresses the limits of our ability to distinguish, and therefore of our ability to know. And there aren't different ways not to know something. Specifying uncertainty numerically is somewhat peculiar, because by its nature we cannot be certain about our uncertainty. That is not a play of words. It wouldn't make sense, for example, to claim that we measured the position x to be 1 centimeter with an uncertainty of exactly 0.5 centimeters, implying that we wouldn't be able to distinguish 1 centimeter from 1.5 centimeters, but we would definitely be able to tell that 1.5, 0, 0, 0, and so on 1 centimeter is a different position. For any continuous quantity, we therefore also must consider the uncertainty of our uncertainty, and the uncertainty of our uncertainty, and so on ad infinitum. The only satisfactory solution is to introduce a continuous measure of our confidence that the measured quantity is represented by a given range of values. This continuous measure is what we call probability. The precise meaning of probability cannot be defined without circular reasoning. Nevertheless, by the preceding arguments, rational thought about the world must use a concept of continuous probability. We can only accept and describe probability axiomatically as an aspect of our relation to the world we experience. We have seen that the need to think in probabilities is not forced upon us by physical theories. It is a necessity due to our limited finite capacity for experiencing the world. The question to theories, therefore, is not whether we need probability or not, but whether our need for probability is only due to our human limitations, or whether there are fundamental limits to experience that apply in principle and to any observer. This is exactly the point where classical physics and quantum mechanics give different answers. I will let my slightly younger self explain the details. The following section uses some mathematical terms. Don't worry if you do not understand every word. At the end, I will give a less technical summary of the most important points. Let's first look at the assumptions of classical physics that were thought to be correct before quantum mechanics came along. I will use the red pen to write down everything that is valid only in classical physics and that will need to be modified later. The most crucial assumption in classical physics is that we can imagine the uncertainties delta x and delta p to go to zero simultaneously. We can imagine to have certain knowledge of the position x and the momentum p at the same time. Consequently, we can represent complete and certain knowledge of the physical situation by specifying a list of values for all the observable quantities. Such a list is said to identify a point in phase space. The idea being that all the possible combinations form an abstract space of a certain geometry, and every point in this phase space represents a distinguishable physical situation. What we really want to do is to predict as yet unknown physical quantities. Quantitative predictions are based on mathematical methods. So the first question is, how do we represent unknown physical quantities mathematically? Let's write uppercase X for the unknown position and uppercase P for the unknown momentum. What kind of mathematical objects are these? Unlike for the known quantities, experience does not directly inform us here, because by definition we never know the unknown, we never experience the unobserved. So we need to postulate an answer. The one thing we can infer from experience is that whatever the mathematical object is, we must be able to restrict it to a definite real number upon observation. In classical physics, we assume that for every physical situation we have a point in phase space representing certain and complete knowledge of the situation. We can therefore model each unknown quantity as a real function on phase space. For every point in phase space, that is, for every physical situation, such a function will give us a certain value of the quantity. And when we have observed the quantity, we can restrict the function to the subset of phase space where it has the observed value. It effectively is a real number on this subset. Now that we have represented the unknown quantities as functions, we can do calculations with them. It turns out that the rules are just the same as for calculating with numbers. A particularly important example is that when we multiply two functions, the order does not matter. X times p is equal to p times x. This is not surprising because in classical physics we can always resolve everything down to distinguishable physical situations, in each of which all the quantities are just numbers. And we know that numbers behave like this. A good way to think about the unknown physical quantities is that they represent the questions we can ask about the physical situation. The known physical quantities are then the answers to these questions. As we are interested in the behavior of the system in the future, we need to introduce the role of time in our description. Let's indicate that the unknown physical quantities may depend on time. For each time t, x of t represents a different question, namely the question, where is the particle at time t? In the classical phase-space picture, this means we have functions depending on time as well as on the point in phase space. Having established these postulates, we can now set up a complete theory of classical physics by giving the equations of motion. There are many equivalent ways to specify equations of motion. I will just briefly sketch one formalism because the details are not so important for the point of this video. First, we specify a function h on phase space called the Hamiltonian. The Hamiltonian usually corresponds to the total energy of the system. It is given by a formula involving the other physical quantities, and its exact form depends on the particular system we are looking at. The equations of motion then give x dot the change of the position with time and p dot the change of the momentum with time in terms of so-called Poisson brackets. These are defined by partial derivatives of these functions on phase space, and right now we only need to know that no further time derivatives appear on the right-hand side. We therefore have a system of first-order differential equations for the time dependence of all quantities. And given the initial condition that uppercase x and uppercase p must be equal to the observed values at the present reference time, such a system of equations has a unique solution. This is a crucial point in classical physics. Once we have exact and complete knowledge about the initial condition, that is, once we know the starting point x0 p0 in phase space, the solution gives us the position x and the momentum p as unique functions of time. It means we can predict their future values with complete certainty. Such classical theories were impressively successful up to a point. For example, they could predict the orbits of the planets precisely. Based on the assumptions and the successes of classical physics, a remarkable mental process took place. Physicists thought the unknown quantities are determined by the known ones with certainty. So why do we even need to distinguish between the known and the unknown quantities? The future quantities are deterministic and just as certain as the ones we know from observation. We may therefore always pretend that someone may already have observed everything. We don't need to distinguish between the observed and the unobserved at all. The culmination of this process was the idea that one could draw a picture of how the physical world really worked. The idea that one could imagine a particle, for example, as a point in space moving along a trajectory, and that its position x of t was just a real coordinate in this space, and so on. The idea that observations were merely the irrelevant copying of information to our senses. This idea that the world would be explained by pictures like this one, that the world was nothing but a mathematical machine built from mathematical functions, became so strong that people assumed it without even being aware of their assumptions. But notice that all of the development of this picture depends utterly on this very assumption here, the assumption that all physical quantities are observable simultaneously with arbitrary precision, and that consequently we can identify the physical situation with a point in mathematical phase space. This whole worldview hinges upon this assumption, and it turns out to be wrong. Thank you, slightly younger self. To recapitulate, as we discussed, uncertainty is needed empirically. However, classical physics assumes that uncertainty is not fundamentally important. It postulates that in principle, we could resolve the world down to fully distinguishable physical situations, in each of which every observable quantity has a certain known numerical value. Together with the deterministic equations of motion, this assumption leads to a remarkable conclusion. Given a certain initial condition, all observable quantities are completely fixed by the equations of motion for all times. In classical physics, it therefore seems unnecessary to distinguish between known and unknown quantities. This also means that the concept of observation, which makes unknown quantities known, becomes irrelevant. For a strictly physical discussion, we still need to interpret and predict quantitative observations, but let us briefly explore the metaphysical implications of classical physics. Just keep in mind that all the conclusions we are now discussing hinge upon the classical assumption that we can in principle get rid of any uncertainty, and that today we know that this assumption is wrong. Let's try to appreciate how weird the classical worldview is and how strange it is to our immediate experience of the world. Although we experience ourselves as conscious and limited observers of the world, classical physics has no need and no place for consciousness. Instead, it suggests that the world can be completely described without any reference to it being observed, and thus without any reference to an observer. But what is such a description even supposed to mean? What is the meaning of the value of a quantity if not as the result of an observation? Furthermore, according to classical physics, there is no essential difference between the past and the future. Both are fixed with equal certainty. Classically, all physical quantities can be identified with eternal mathematical objects that solve the equations of motion for a mysteriously given initial condition. These simultaneously physical and mathematical objects appear to exist in an absolute sense that nevertheless cannot be defined. Granted, the classical worldview has one feature that strongly appeals to many. As it assumes the physical world to be fully and simultaneously knowable, this worldview allows us to imagine a complete picture that represents the world just as the graph of a function represents a mathematical function. Having such a mental picture is synonymous to what many people call understanding the world, because we are so used to thinking visually that we sometimes equate pictures with understanding. But note that calling the classical picture our understanding of the world is ironic, because the price to pay for this picture is the complete lack of any framework for acknowledging, let alone reasoning about, our own conscious experience of the world. So much for the weird classical metaphysics. I mainly discussed it because I think too many people are unjustifiably enamored of the obsolete classical worldview, and it keeps them from appreciating quantum mechanics. Empirically, the ruling is clear. Both classical physics and quantum mechanics make predictions about observable quantities. The predictions of classical physics are contradicted by experiment. The predictions of quantum mechanics are confirmed by experiment. Classical physics is wrong. Even more generally, it has been shown that all physical theories, which, like classical physics, assume local realism, are refuted by experiment. In other words, all theories that purport to give us a complete picture of the observable world are known to be wrong. We have no choice but to give up the idea of understanding the world in the sense of forming a complete and correct mental picture of it. Such a picture does not exist. We must settle for a more general sense of understanding the world that focuses on the mutual relationships of observable quantities. In the next episode, we will see how quantum mechanics represents observable quantities and how it changes our assumptions about the fundamental limits of observation and knowledge. If you have any questions about this video, please post them in the comments below. If you don't have any questions, please comment anyway to let the algorithms know that this topic is interesting to people. Also, please share the video so we can all work together to somewhat reduce the confusion surrounding quantum mechanics. See you next time!